Welcome, everyone. Thank you so much for joining us for the Battery Insiders podcast here live from the Battery Show North America in Detroit. And I'm extremely delighted to have a fantastic guest with us today, Celina Mikolajczak, who is the Chief Battery Technology Officer at Lyten. And yeah, today we're going to talk about sulfur technology, sulfur batteries, but also quite a bit more than that. My name is Simon Engelke, and I'm the founder and chair of Battery Associates. I'm extremely excited you're joining us for today's conversation. So Celina, wonderful to have you.
Well, thank you so much for inviting me.
Absolutely. And I mean, really, one thing is, you have been involved in a lot of different technologies. There's quite a few things. I think not that many people can say that. Really look at all the topics you've looked at, BESS, the lithium-ion batteries, and solid state, and our sulfur with Lyten. We could share a bit about your perspective on these different topics and some of the milestones you have seen.
Sure. I've been doing batteries for 25 years. That's why I've done a bunch of things. I've kind of really grown with the industry and worked as the industry has grown on, the topics of the day, which is really quite a, luxury and a pleasure, right? I started in the industry back in late 1999, early 2000. At that point, lithium-ion was really seeing, massive growth into laptops, right? And then into cell phones, but they weren't really into cell phones yet, right? A lot of questions about battery safety and about quality and safety and battery failure at the time. I was working at Exponent Failure Analysis. I started doing failure analysis on batteries. And, there wasn't anyone to teach me how to do that, right? This was just a need that had come up from the industry. So I spent, a decade doing that, right? And in that time frame, cells evolved. When I started, there was small prismatics, and there were 18650 cylindricals. And when I left Exponent, most of the consumer electronics guys had moved to pouch cells. That was super hot. And cylindricals seemed to be like, in kind of their going down, except I went to Tesla where we were only using cylindrical cells, right? And then watched as cylindrical cells came back into favor as, Tesla ramped Model S and then Model 3 and Model Y. So I've kind of seen, work with the industry and really been focused on where the big problems are. That's where I've gone to. So when I started, it was consumer electronics, the failure side. Then I went to Tesla because I was starting to see the same problems over and over again, right? And it wasn't that interesting. And then here comes Tesla. And now the challenge becomes, can you take something that you developed for consumer electronics that had maybe a 3 to 5 year life? Could you take it to 8 to 10 years or longer? Could you make it into a car and imbue the car with the safety systems to make it really safe, right? To the point where, I've got a car at home. I've got a Model S that's vintage now. I've got a Model Y that's newer. And I got 3 Powerwalls in the garage. So I probably have about 200 kilowatt hours charging in my garage every day. And, I've burned a lot of cells. I've done a lot of safety testing. I'm calm. I'm like, yeah, I'm good with all that in my garage, right? That comes from all the work we did on quality, on safety testing, on understanding what causes failure and mitigating that to make really a car that works and that's compelling and, really drive the industry to say, yeah, we can make electric cars, right? So, and, when I started at Tesla, a lot of people thought this thing was never going to work. I could read the press every day and there would be boosters that said, yeah, electric cars are coming, and other people saying it'll never happen. It's a total scam, right? And, just watching that press going back and forth, and then seeing the community. I mean, we had to really create the supply chain out of nothing, right? We would go, see suppliers for parts for our electric car, and they weren't necessarily even automotive suppliers, right? Or they might be automotive suppliers, and we'd tell them what our volumes were, and they'd be like, so is that per month? And we'd be like, no, that's for the whole year. And they were like, wow, you're really small time, right? And just don't even want to talk to us. And then, sitting here today on the Detroit Battery Show, I mean, I've heard there's 11,000 exhibitors and 19,000 people. Unimaginable in like 2012, right? A little more than a decade ago. No one was going to talk to us. And we were creating these suppliers. And here now we have this massive industry that's really focused on electrification and EVs. So big changes. I was at Tesla for quite some time. I wanted to do more, so I went to Uber and I designed battery packs with a team for micromobility and for aircraft, and got a taste of being a pack designer, which was different and interesting. Uber divested itself of that hardware business. Okay. I went to Panasonic to the cell factory and ran engineering at the Gigafactory, which is an education that, anyone that's doing cell making or wants to do cell making, you need to go get that education, right? Because what you learn in a full-scale, high-speed cell manufacturing facility is, I think, impossible to learn from reading papers or attending conferences or, from any kind of other background. You have to live it, be inside the factory, feel the buzz, feel the pressure of the fact that it's going 24/7. It does not stop. You do not to get to stop. You might slow some things down. You might stop a machine. You might have to fix some stuff, but it's all under that pressure of continuous production, right? And that if you stop, you're never going to get those production days back again. You will never recover that revenue, and you just lost your profit margin, right? So, that pressure, that ongoing dynamicism, that the factory doesn't go to sleep, the problems don't stop at 5 p.m., right? They just keep going. And how do you put a team together that addresses that? How do you keep that going? Some of it comes out of your cell design, right? Because your cell design has to be fundamentally manufacturable. And then you have to have the equipment that's going to run, and it's going to run continuously for years at a time. And yes, you're going to have to maintain it periodically. You'll have to take it down. You'll have to put up other equipment. But again, you can't stop, right? That continuous nature of the whole manufacturing process, it's hard. You can't really get it until you live it, right? And you live under that pressure. Once you do, you start looking at the world a bit differently, and when, and I came back into the Bay Area and I went to QuantumScape and worked there for a bit. And then I came to Lyten to do lithium-sulfur. And, the reason I came to Lyten was I looked at this chemistry and I said, okay, this thing solves some of the big problems we're having now, right? It solves our supply chain problems. And, you can say, well, there's the Chinese geopolitical problems. Yeah, that's fine. That's one problem. But there's also the fundamental problem of there's a limited supply of nickel. And to get more of it, you have to do some increasingly, environmentally questionable things, right? And that's a problem. And then even if you do those environmentally questionable things, even then, do you have enough nickel to really electrify everything? And the answer is not a convincing yes. The answer is more like, no, not really. So, when I look at lithium sulfur, I'm like, wow, this is a technology that, okay, I can make it on standard equipment. I can foresee running this in a real factory. The price is going to be lower, so this is a candidate for electrifying everything. And I don't have a raw materials problem per se. I'll have plenty of challenges. I'm going to have to scale a supply chain just like anyone else. But from a fundamental perspective, where do you get sulfur? Where do you get lithium? Where do you get carbon? These are straightforward answers. And they don't create a whole environmental problem at the same time, right? So, it's been a really interesting journey, but it's been a journey toward the harder and harder problems, or the problems of the day, right? Because, once people have figured it out, then you're just kind of doing stuff over again, and then it's boring, right?
So I think what I can tell is you're a problem solver. That seems to excite you, which I very much can relate to.
Yeah, I mean,
definitely people like you to address these challenges and going there. And I think what's kind of interesting how you cross-pollinated, I feel like, a lot of these different industries, right?
Yeah.
Bringing your expertise into them. So I think that's super fascinating.
Well, it's kind of fun to do something multidisciplinary like that, because batteries are very multidisciplinary. They always have been, right? People like to say, oh, I want to go study electrochemistry, and that's great. But the electrochemistry in a battery is only one starting point. There's all these other things, and you have to take that all in. And isn't that the most fun problem, when you have to take all the experience, from all these different areas and bring it together. That's a fun problem.
And maybe now, if you just think about that, right? So we mentioned these different technologies you've been working on, from lithium-ion batteries to also a bit of a look at solid state and now with sulfur. Are there like some common topics, or is it like, common challenges and scale up and manufacturing, or is it all quite different?
There's a lot more commonality than you think. Okay. They are very different technologies. But some of the questions still remain the same, right? The scale is huge, right? So you really do have massive supply chain. You can't be thinking in small amounts, right? You have to be thinking these large amounts and face into that abyss, right? Because we're talking about electrifying, changing basically our transportation infrastructure out of a petroleum-based industry into an electric industry. If you think about the scale of that and really start looking into it, you realize, wow, there's a lot to do here. There's a lot. So the scales are huge. The factories are daunting, right? You walk in and you're like, you're just taken aback at how big everything is, right? So that's a big piece of it. The other thing that is true for all these chemistries, the tolerances are very, very small. So in batteries, you measure your tolerances in microns, okay? And to produce at scale, you measure takt times in microseconds, right? So, and why does that matter? Well, in the automotive industry, right, when you make cars, right, a car or frame or a piece of thing comes into a station, and then people like jump on it and work on it and do some stuff, and then it moves on. So usual takt time is something on the order of like a minute, minute and a half, maybe, but your takt times are in minutes or fractions of minutes, right? And your tolerances, you might measure in fractions of millimeters, right? Like to make sure that all the fit and finish of the car is right. So that's kind of where you're working. When you go to cells, you can't touch the cells anymore. You have to have the machines touch the cells. They have to do it at speed, and they have to be entirely precise every time. And that's true whichever chemistry you go to, right? So that's what makes it so hard. And that's what makes it so different from all the other manufacturing that we're kind of used to thinking about, right? Like, for a long time, I think a lot of people have in their minds the old idea of a factory. There was like a Lucille Ball episode, right? I Love Lucy episode where she and the other one are packaging like candy or doing something with candy. And you see the like assembly line and they're touching, right? For a lot of us, that was in our mind for what a factory is. And the reality of a modern day factory, it's very different. And a cell factory is really, really different.
It makes a lot of sense. And I think also very important to educate people on that, right? And I think people understanding what a factory of today is and also what it might look like in the future.
Yeah. Yeah. I think a lot of people are like, well, it's not manual anymore. You're not going to need these workers. It's like, no. When you have equipment that's pushing hundreds of thousands of cells through it every day, you need equipment specialists. You need guys that really understand maintenance and they understand wear and they understand, okay, if I push 100,000 cells through here, I'm going to have wear in this location, that location. I'm going to have debris that's just, little fine dust that just builds up every bit in this location here and there. This is what I'm going to have to do to take care of this machine. That's high skilled labor. That's not entry level, hire a guy at a high school, put him on the production line thing. This is craftsmanship. And I always view it as, look, cell making is an opportunity for the, middle class and the blue collar worker to come back to craftsmanship, to come back to a level of expectation of the job that is not, at some low level anyone could do it, but it's a level of, real pride, right? Which, it's kind of different than most people are thinking about.
I fully second that. Yeah, we have a few initiatives on this regard, so
yeah,
I couldn't speak a little more. Another topic we get a lot of questions about is scrap rates.
Oh yeah. Oh my God. Yeah.
It's like one of the best, protected data point, it feels like, in the industry, but the one everyone wants, no one talks about.
Yes.
So maybe, I don't know if you can share a bit of, perspective on this, like what is a great scrap rate? Like where are we today? Things like that.
Well, it depends, right? Depends who you are and depends what you're making. Um, I will tell you that if you have a lot of scrap, you will not be profitable. Okay. Like really not. And then, what's a good scrap rate? What's a bad scrap rate? That depends on the price margin that you're commanding with your customer, right? If you've got a big margin on the sale, sure, you can have a big scrap rate, right? But if your margins aren't that big and you're working at volume, which is really where the automotive industry is, right? They're not making boutique sales. They're making millions a day, right? Uh, If you're making millions a day, you don't have huge margins on that. You're doing this in volume. If your scrap rate starts mounting, your profits start disappearing in a heartbeat, right? And it's just a lot of physical scrap, right? If you think about it and you say, well, I've got a coating, all right, and my coating's a meter wide, okay, and I have a bunch of cathode on it, and it's a meter wide because I'm going to slit this down into pancakes, right? Okay, how how quickly am I going to fill up my scrap bins if I let 50 feet of this thing go by with a problem? And it goes by at 50 meters a minute, right? So if I let it go a minute with some big issue that I have to then cut that out, I've filled my scrap bins, right? Now, is this huge money relative to what you're doing every day? Doesn't matter. It's still huge money, right? You look at that and you're like, wow, I really don't want to do that, right? So, yeah. So, people are protective of the scrap rates because it tells you a lot about their margins, okay, and what they're allowed to be, right? But, I, I can't, like, you cannot survive as a going business. If your scrap rate's at like 10%, you're done. You're not never going to happen, right? Okay. So that's just like a non-starter. Now, that might be your scrap rate when you're ramping up the equipment and you've got all kinds of problems, but you can't be there long, right? Because, the other thing about this is, let's assume your scrap, that 1 meter wide, 50 feet or 50 meters of this thing, right? Well, that's a lot of money, just straight up, right? So if you don't have revenue to back that up, you're out of business in a heartbeat, right? So this is where everyone's trying to knock the scrap rates down because in a gigafactory, you can make a ton of scrap so fast and it'll cost you $1 million in a day or something, right? You're like, oh my God, right? So that's where you work, and that's where some of the pressure comes too, because let's assume you've got some equipment that isn't working quite right. Are you scrapping the material? Are you not? If you if you're scrapping a lot of it, you'll shut down the line. If you're scrapping a little bit more than normal, should you still shut down the line or should you keep running and take the scrap hit? And this is where the factory manager, the factory leader is making these decisions in real time every single day, every day. So,
And it's as you said, right? We have seen, especially the ramp up can be terrible, the scrap rates, right? Going
oh yeah,
to 50, 80, whatever percent.
oh yeah,
I've seen it all.
oh yeah.
So,
So you can't live there for very long. Like,
or you need really, really deep pockets.
yeah, yeah.
I think it's difficult. Thanks on that. Another topic also, looking at sustainability, right? I think it's a big topic, especially in European markets, but I think also over here, efficiency, right? Like energy requirements, monitoring,
Yeah.
things like that. Is anything interesting you have seen in this regard? Any evolution you have seen?
I mean, I think people are thoughtful about this. People in the battery space have been thoughtful about efficiencies for a while, because again, you're working with margins, right? If you're using too much electricity, you're taking that right out of your profits, right, on your factory, and that can be substantial, right? So people have been thoughtful, um, but there's continuing ongoing pressure with the materials people are using. I mean, when I started in the industry and all the cells were consumer electronic, they were all cobalt oxide based. Okay. Which is great chemistry. Oh my God, it was fantastic, right? It helped in so many things. But it's a conflict mineral and you can't get that much of it. Now, when lithium-ion batteries were starting out, no one thought too much about it because cobalt was kind of a byproduct. And so it was reasonably achievable. No one was worried about it. But then as the industry grew, suddenly people are like, wait, we can't have this cobalt. We're creating these terrible environmental conditions, these terrible social conditions. So people start moving away from cobalt, right? And that's where you got the high nickel chemistries. So suddenly then, I started a Tesla and CA. There was a little teeny bit of cobalt in there, but mostly it was nickel and aluminate. All awesome. Great. We solved the cobalt problem. Great. A decade later, we're looking at this and going, there's not enough nickel, right? So now we've got to go solve that problem. So you kind of see the continuing evolution as the industry scales, as the demand goes up relative to, the materials that are out there. So that's pretty cool to see.
That's also maybe one thing, right? When you optimize for one topic, because now, right, I mean, another topic is LFP, right? Which also Tesla and others really have pushed really strongly, where then we replace nickel.
Yeah.
Then others, even I've seen China a lot of development and India and other regions on sodium, right?
Yeah.
Really keep replacing all kinds of things.
Yeah.
And like if you like bring in a new technology like sulfur, right, where you optimize one thing, but the market is also continuously shifting, right? Like your reference, your peers are shifting too.
Yeah.
So I think how you stay like, as relevant, give you one example, right? Because I've seen the sodium-ion, all the reasoning or like all the argument for it was cost, right?
Yeah.
I remember the days when people are like, oh, sodium's going to be cheaper. And now we're in this interesting position where suddenly sodium is not cheaper. Actually, lithium LFP is cheaper. And suddenly the story is all about, oh, but this might be safer, like supply chains, like more robust and things. And so it's interesting to also see how technology, the story around change. And honestly, I started my career on sodium-ion. I think there's still a place for it, right?
Oh, yeah.
But the story is different than what it has been. And maybe it's cheaper again in 2028 when the lithium price goes up and all these things, right? So I guess just from your perspective, like even with the sulfur, right? Because now you mentioned you can, just true, you replace the nickel topic and still do really high performance.
Yeah.
But do you maybe think one day, if sodium becomes a big topic, you need like sodium sulfur? Or
no. But, here's the thing, like lithium-sulfur is appealing to me because it really is the cheapest, right? The cathode is incredibly inexpensive, incredibly abundant. Lithium, I know people talk about lithium as supply chain, but I really think as a community, we haven't really started tapping real lithium supplies. We've gotten the really cheap ones, like, out of the Atacama Plateau, where like the sun and the wind do half the work for you. But I really think subsurface brines are an answer there that's going to be, if we pursue it, cost effective, should drop the price of lithium substantially, should stabilize world lithium supplies. It's going to take someone to decide to do it. People ask me, well, why haven't the oil companies done it already? I would think the oil companies would want to do it. I've heard that, they're like, well, the profit margin isn't that big compared to doing oil. And I'm like, well, that's a problem, isn't it? But this should be fixable is what I'm saying, right? And this should be something where lithium should be very abundant as a raw material.
And do you think because now you have seen quite a few different chemistries in your career, do you think we need a different chemistry? Or do you think there's going to be another chemistry which really going to, change the entire market?
Well, so I've seen a bunch of chemistries come through, right? I mean, when I was starting, the cell phones were still nickel metal hydride based batteries, right? And, we still saw some of those in laptops and, that was what was in cars. That was the Prius, right? And the power tools were still using NiCads. And, cadmium's another one of these things that we'd really rather not have running around in our communities, right? So we've seen that kind of evolution, right? And I think battery chemistries do evolve. So I look at lithium-sulfur coming in, it's not going to displace high nickel chemistries. People will still use high nickel chemistries. People will still use LFP. Sulfur will take another big chunk of the market where it's really well suited. Those other chemistries will stay where they're well suited. And, it's going to be about cost and performance, the usual things, right? There's not that many other chemistries left out there, right? When you look at the electrochemists, what do you get to get high power? People talk lithium air. Challenging, really challenging. When you talk about lower energy, lower performance, lower energy density chemistries like LFP or, the iron air batteries that Form is doing, they'll have a place too, right? As we electrify, but they're going to they're just going to have a different place in the market, right? Where you're going to want to do those things. So I feel like I, I don't see us, I see us just expanding the market, having more needs, more variety of needs, and developing chemistries that fit those needs well, and then continuing that expansion.
And also, I think there's a lot. I think one thing that really always amazed me to be, you mentioned earlier, be places in here where you see all of these companies doing all kinds of things. Even like if you maybe do like a filtering here, maybe it's 90% lithium-ion or something.
Yeah. Oh, yeah.
And all of them have place, right?
Yes.
Optimizing their specific topic.
Yes.
Even just this one.
And we hope all of them are profitable, but but they're all like legitimate business interests, and it's thousands, right? So there's so much there. People are like, oh, it's just electrification. I'm like, no. You're talking about the entire transportation sector for the world. That's a lot there. A lot.
And even going aviation and topics, which also have been quite interesting with sulfur. I remember quite a few approaches has been on these applications as well.
Yeah, anywhere where lightweight is at a premium. So aviation, satellites, even like micromobility, when you've got a heavy battery pack and someone wants to take a scooter up the stairs to their apartment, well, if you lighten up that battery pack, it makes that scooter a lot more appealing, right? So there's lots of things like that we're going to see. But we're going to see new applications too. I mean, people are talking about, applying electrification to ships and, watercraft and a lot more stationary. And then there's this whole AI revolution that's going on that takes huge amounts of power. And the only way people are really going to do it is if they can use renewables. Well, you don't just use renewables, you use renewables plus battery. So which chemistry is going to be great for that? Well, whichever chemistry is going to be great for that sector is going to suck up all those batteries, right? And it's going to leave another big hole where something has to fill. So there's a lot of this going to be happening.
And maybe for our listeners, right, you might be curious about sulfur and like, what's your pitch? Like, which application do you think are like best suited for sulfur batteries?
Yeah, so lithium-sulfur has really two big wins to it. The first one is it has a roadmap for energy density that gets it to twice the gravimetric energy density of high nickel chemistries, right? So are we there yet? No, but we're getting close. We're at par with conventional lithium-ion, like good conventional lithium-ion.
Where roughly number-wise?
So like, in the 200 to 300 watt-hour per kilo, right? So we're making those cells today, and we've been at this like 5 years, okay? That's taken 30 years to get to in conventional lithium-ion. So we've got a lot of low-hanging fruit and roadway ahead of us, right? So you're looking anywhere where energy density matters, which means weight versus range, right? Gravimetric, right? Heavy trucks, aircraft, satellites, all those things where weight matters. Great area for lithium sulfur. The other big benefit is cost, because the supply chain is so straightforward and sulfur is so cheap, right? You're always going to be substantially cheaper than any of the nickel chemistries and the LFP chemistries. Substantially cheaper. So you want to have electric cars for everyone? You want to have three-wheelers that are inexpensive for everyone? Your cell is lithium sulfur. That's how you get there, right? So, when people talk about the average price of, batteries coming down, it's not going to happen with nickel or LFP. It's because those analysts have been pricing in lithium sulfur into that roadmap, right? So that's where you're like the everyday person's car, that's going to be lithium sulfur.
Maybe just understand, right? Because you have seen this remarkable price reduction over the last year, right?
Yeah.
Like what happened, just like amazing.
Oh yeah.
And also really, I think, took a lot of people, and of course, there's many drivers and overcapacity and raw material and lots of things, right? But now looking at something like $50-$60 per kilowatt hour, and people are like, whoa, what happened? That was 100 a year ago. And of course, there's caveats and might go up and these things. But
yeah.
Just understand, like, because I did some other interviews and was, about different manufacturing processes, and they were talking about we can do 10% price reduction, right? That's our goal on a cell. How about you? Where do you think like sulfur could end up from a cost perspective? Is that significant cost reduction? Is there like any magic number you have in your mind, or where you want to get to, or where you think?
Where do I want to get to?
Where do you think it's possible, right, from a technology perspective?
long term, yeah, long term, I think we can get below $50 a kilowatt hour, right? I do think a lot of the stuff that you're seeing right now is subsidized. I think it is not a real pricing. And that's good and bad thing. I mean, the good thing is the price is so low. As a friend of mine pointed out at dinner, price is so low, people are considering electrifying more things, right? Because suddenly it's like, hey, wait, this is not too expensive. We can do these things, which is great. At the same time, when it's artificially too low like that, then there's a shock where the price goes up again, and then everyone gets kind of into a bad place, right? So, but I think, if you look at real price, real BOM, real cost to produce, I think lithium sulfur will be cheaper than everything else. And, what's that number look like? Well, right now that looks like you should be able to get under 50 in the long haul. Not tomorrow, not this decade, but long haul, yeah, you should be able to get there. Um, the other chemistries don't have a pathway to that. Not really. If you look at what it takes to produce the materials, they don't get there.
Awesome. And then maybe one last thing also on the stability topic, right? Which is something where so far I think it's a lot of questions we've received. Like, what do you see on that, like life cycle, these kind of topics from sulfur compared to other chemistries?
Yeah. So, from a stability perspective, I mean, lithium sulfur, the hard part is always the cycle life, right? But we've been making really strong strides in that, and we think we can get cells that are going to be very acceptable to the market. The other thing about sulfur is the carbon footprint for these cells is about half that of conventional lithium-ion, right? So, and that's even now, today, right? We get up in energy density is going to be even lower than that, right? So the cells, the environmental impact on the cells just starts off as substantially less impactful, right? And then, do you want to recycle these cells? How hard is it to recycle? The thing about lithium sulfur is, you got sulfur and lithium in there. And the only thing that's worth anything is the lithium, right? Which one has opportunities to recycle, right? But it's not like if you throw if you're throwing away these cells and they end up in a landfill, right? If you've got nickel and cobalt in the landfill, that's a real issue, right? And you really, really have a problem with that. A lithium sulfur cell is like, it's not, you're not like so freaked out about it, right? So you say, well, can I recycle it? Yeah, you can. It may or may not be worth your time. You probably will be eventually, but then it's also not that hard to recycle either.
A similar bucket, I would say, to LFP, right? So, I mean, also you also lithium in there as well, and there is approaches, and I think it has to be recycled, right? Like from an approach, and will be. But it's a big topic, right? I think where how these things are connected, right? That people don't think about, and I really appreciate that you have this in mind as well.
Yeah.
That there's reached a solution as well. So that's super exciting. Honestly, as someone that's been following also your work, but also of the sulfur as well. I think it's one of these really interesting technologies which could unlock a few things, right? You said from a cost perspective and from an application perspective, which is, I think, really exciting. I think just from a problem set to address two at the same time.
Yes, exactly.
Try to optimize for both.
Yeah, exactly. Well, it gives you that margin, right? So you can kind of work in the space and make some mistakes, because every time you try and scale a new chemistry, you run into some real difficult times. You run into some really bad scrap rates, right? You have to solve those problems. So you got to give yourself some room. So it has some room to allow that development. And yeah, I think, this is kind of, I think we're at a point where lithium sulfur can now take off and become that next great chemistry where, people have tried it on and off periodically for a while and it's not really taken off. This is the time.
Excited to follow this journey, Celina. I really, really appreciate your time today and giving us insights for our audience of talking about sulfur, but of course also about manufacturing, which I think two really important topics. I want to say big thanks also for all of you listening today from the Battery Insiders podcast community. And I hope you had a really good time here hearing us today live from the Battery Show in North America in Detroit. Big thanks also to Informa Markets for having us here. And of course, massive thanks to you, Celina, for sharing your insights. And again, super excited what you already have done. Very excited how you're going to address the sulfur topic now. Let's see what you're going to address next. But for now, really excited to see your journey there.
Thank you so much. Thanks for inviting me.